From knowledge bases, to ontologies. This is episode 7, Reasoning. All the way through this series, we have kept using one quietly magical word, reason. We built an ontology, populated it with facts, and then said, almost in passing, that the engine infers, the engine classifies, the engine checks. So today we finally open that engine up. Reasoning is the single thing that separates an ontology from a mere database. A database faithfully gives you back exactly what you stored, and nothing more. An ontology gives you back something larger, the conclusions that logically follow, the facts you never actually wrote down. Let us see how that works. So here is the heart of it, in a single line. Reasoning turns explicit knowledge into implicit knowledge. You assert a handful of facts and rules, the explicit part, the things you actually typed in. And a reasoner then derives everything else that must be true as a consequence, the implicit part, which can be far, far larger than what you started with. In logic, this is called entailment. If your stated facts make some new fact unavoidable, then the ontology entails it, and a sound reasoner is guaranteed to find it. This is why we keep insisting that an ontology is alive. It does not merely store knowledge, it grows it, deriving, from a small seed of statements, the whole tree of everything they imply. A reasoner has two great jobs, and very nearly everything it does is one of these two. The first is classification, sometimes called subsumption. The reasoner works out the complete class hierarchy, figuring out, for every pair of classes, whether one is a subclass of another, even where you never said so directly. It builds the family tree of your concepts, automatically. The second job is consistency checking. Here the reasoner asks one simple, vital question: do all of these axioms actually hold together, or have you stated something that can never be true at once? If your ontology hides a contradiction, the reasoner will surface it. Classification organizes your knowledge. Consistency checking guards it. Between them, that is most of what reasoning means. But how does the engine actually do all this? Underneath, an OWL reasoner runs on description logic, that decidable fragment of formal logic we met 2 episodes ago. It uses an algorithm, most often something called a tableau method, which systematically tries to build a model of your ontology, a consistent world in which every axiom holds. If it can build one, your ontology is consistent. If every possible attempt collapses into contradiction, it is not. And here, at last, is why we cared so much about OWLDL staying decidable. Decidable means the reasoner is guaranteed to finish, and to return the right answer, sound, so it never lies, and complete, so it never misses. That guarantee is the whole reason we accept the discipline of the logic. Let us watch a reasoner actually think, with a tiny example. We assert just a few things. Professor is a subclass of staff. Staff is a subclass of person. And the property supervises has its domain set to professor. Then one bare fact: Dr. Lee supervises a student. Now watch the cascade unfold. Because Lee supervises someone, and supervises demands a professor, the reasoner concludes that Lee is a professor. Because professor sits under staff, Lee is therefore staff. Because staff sits under person, Lee is a person. From that one asserted fact, 3 brand new ones simply fall out, not a single one of them ever typed by a human. This is the cascade of inference. Each conclusion quietly unlocks the next, rippling up the hierarchy, until everything that must be true, simply is. That cascade grows dramatically richer once you start describing how your properties behave. OWL lets you give a property a character, and the reasoner faithfully honors it. Declare a property transitive like ancestor of, and if Anna is an ancestor of Ben, and Ben of Carla, the reasoner instantly knows that Anna is an ancestor of Carla, and onward, all the way down the line. Declare a property symmetric, like married to, and stating it once, in just one direction, hands you the other direction for free. Declare 2 properties inverse, has parent and has child, and every fact about the one quietly becomes a fact about the other. You describe the shape of a relationship a single time, and the reasoner then applies it everywhere, forever. There is one more kind of property character, and it does something subtly different: it catches mistakes. Declare a property functional, meaning each thing can have at most one value for it. A person has exactly one biological mother. Now, if your data somehow claims two different mothers for the same person, the reasoner does not simply shrug. Under the logic, it concludes that those two mothers must in fact be the very same individual, or, if you have separately stated that they are different, it raises a flat contradiction. So property characteristics quietly do double duty. They infer the new facts you wanted, and they expose the bad facts you did not. Reasoning, it turns out, is every bit as much about finding errors as it is about finding answers. Let us press harder on that error-catching power, because it is one of the most genuinely useful things a reasoner does. Remember disjointness, from the formal stack, declaring that two classes can never, ever overlap. Suppose we state that undergraduate and graduate are disjoint. Now imagine someone, somewhere in a dataset of 1,000,000 rows, accidentally asserts that one particular student is both at once. You would never find that slip by hand, not in 1,000 years. But the reasoner, quietly checking consistency, hits the contradiction the moment it runs, and tells you exactly where it lives. The same holds for cardinality. Claim a course has two primary instructors where the ontology permits only one, and the alarm sounds. In a large, constantly evolving knowledge base, this automatic hunt for contradictions is worth its weight in gold. Now for the one idea that trips up almost everyone arriving from databases, and it is absolutely essential. Ontologies reason under the open world assumption. A database, by contrast, lives in a closed world. In a closed world, if a fact is simply not present, it is taken to be false. Absence itself is treated as proof of negation. Ask a database whether Bob is a vegetarian, and if it holds no record saying so, it answers, confidently, no. An ontology flatly refuses to do that. Under the open world assumption, if you have never stated whether Bob is a vegetarian, the honest answer is not no, it is unknown. The world may simply contain facts you have not written down yet. That single shift, from not stated means false, to not stated means unknown, changes how every last conclusion is drawn. Master it, and the reasoner stops surprising you. Let us lay the whole picture out side by side, with one small worked ontology. On the left, what we asserted, our explicit input. Bird is a subclass of animal. The property eats has domain animal. Robin is a bird. And Robin eats a worm. That is the sum total of what a human actually typed. On the right, what the reasoner adds, the implicit output. Robin is an animal, because every bird is one. Worm, being eaten, lands in the range of eats. And the entire class tree is now organized and verified for you. Notice the shape of the two columns. The left is small, and finite. The right is larger, and it was generated entirely for free. That gap, between the two columns, is precisely the value that reasoning creates. In practice, of course, you do not write a reasoner yourself, you pick one. There is a mature family of them, each a serious feat of engineering. Hermit and Pellet are full OWLDL reasoners, handling the rich, expressive logic. ELK is blisteringly fast, but only for a deliberately simpler profile. And that word, profile, matters a great deal. OWL defines several official profiles, EL, QL, and RL, each one a carefully restricted slice of the language, chosen so that reasoning over it is not merely decidable, but genuinely fast, and able to scale. It is exactly the trade-off from episode 5, made concrete. Give up a little expressive power, and you buy back enormous speed. The right reasoner, and the right profile, is an engineering choice you make fresh for every project. There is also a choice about when the reasoning actually happens. One option is to materialize, to run the reasoner up front, compute every single implied fact, and store them all alongside the originals. This is forward chaining, and it makes later queries lightning fast, because the answers already sit there, waiting to be read. The other option is to reason at query time, to keep the data lean, and work out only the inferences you need, at the very moment a question is asked. This is backward chaining, and it keeps storage small and updates cheap. Materialize for read-heavy systems that rarely change. Reason on demand for data that shifts constantly. As with everything in this field, it is a trade-off, chosen to fit the precise shape of your problem. So why does all of this earn its keep? Because reasoning is what makes a large knowledge base trustworthy, and useful, at real scale. Consider medicine. SNOMED CT, the great clinical terminology, holds hundreds of thousands of concepts, and a reasoner classifies that entire hierarchy automatically, a feat no human team could ever maintain by hand. Consider data integration, merge two databases, and a reasoner can infer where their concepts genuinely line up, and flag clearly where they clash. Consider sheer quality, across a sprawling, ever-growing ontology, the reasoner silently hunts down the contradictions that always creep in over time. Inference, classification, consistency, these are not academic luxuries. They are exactly what lets a formal knowledge base stay correct, and stay coherent, as it grows to a size no single person could ever hold in their head. So that is reasoning, the engine that turns a mere record of what we know into a living system that derives what we never said. Entailment, classification, consistency, the open world, and the family of reasoners that make it all run. It is the deepest expression of the symbolic tradition, knowledge you can not only store, but actually prove. And that sets up our finale just perfectly. Because the great story of this very moment is the meeting of two worlds, the symbolic, which reasons and proves, and the neural, which reads and generates. Next time, Episode 8, Neurosymbolic AI and Agents, where the two halves finally come together, and we map out the road ahead. See you there.